A 33 billion-ton interstellar object, 3I/Atlas, is about to skim past the Sun at nearly 70 kilometers per second. But this encounter could rewrite everything we know. For 16 days, every major telescope on Earth will be blind as the object lines up almost perfectly with our planets, a path so precise it almost never happens by chance. If 3I/Atlas uses the Sun to stop, we'll miss the moment that changes our solar system. What could really happen during the blackout? Every major observatory faces a hard shutdown. From October 22nd through November 7th, telescope safety protocols force a total blind spot around the Sun. The James Webb Space Telescope, Hubble, and even ground-based giants like Keck and VLT are programmed to avert their gaze. These rules are not optional. Pointing sensitive optics near the Sun risks burning out billion-dollar instruments in seconds. NASA's operations team locks out observation windows while ESA's network follows suit. For 16 days, not a single sanctioned asset on Earth or in Earth orbit is allowed to track 3I/Atlas as it races behind the Sun. This isn't just a technicality. By design, the blackout is absolute. Safety software overrides any attempt to override the block, no matter how urgent the request. Even the most advanced robotic telescopes are forced to power down or redirect. The James Webb's mission planners have already scheduled a complete withdrawal from the solar exclusion zone, while Hubble's gyros are set to hold steady, waiting for the all-clear. Astronomers forced to watch the clock can only collect data up to the last safe minute. Mars orbiters and solar probes might catch a glimpse, but their coverage is narrow and uncoordinated. For the rest of the world, the blackout is total. The moment 3I/Atlas crosses behind the Sun, everything that happens, any change in speed, direction, or structure, will unfold in silence. The world's best instruments are locked out, not by choice, but by hardwired rules. For over 2 weeks, the solar system's most unusual visitor is left unwatched, and speculation begins to fill the void. On the night of July 1st, 2025, the Atlas Survey's automated system flagged a moving speck in the southern sky. At first, nothing seemed out of the ordinary. A faint, fast blur, barely distinguishable from the background stars. But as the data streamed in, the numbers refused to fit the usual script. This object wasn't looping around the Sun like the familiar comets cataloged every year. Its inbound velocity clocked at 55 kilometers per second, far too fast for anything born in the solar system. Astronomers at the Rio Hurtado Observatory double-checked the orbital solution. The trajectory was unmistakable. 3I/Atlas was coming from interstellar space. What truly set it apart wasn't just its speed, but the path it traced. Instead of plunging in from a random angle, 3I/Atlas slipped almost perfectly along the ecliptic, the same thin plane where every planet orbits. Its inclination measured just 5 degrees, a razor-thin tilt compared to the wild entries expected from interstellar wanderers. The odds of such an alignment are vanishingly small. Most objects from beyond the Sun's reach arrive at steep, unpredictable angles. This one threaded the solar system's highway nearly flat, but in reverse, a retrograde drift against the usual planetary traffic. For the Atlas team, the implications landed fast. An interstellar object matching the solar system's plane is like a dart thrown from across the galaxy, landing edge-on to the bullseye. Some began to ask, what are the chances of that happening by accident? As orbital models tightened, the geometry suggested something else, a path that would give any traveler the best shot at using the Sun's gravity to slow down. And with the blackout window closing in, every new data point only deepened the puzzle. At the heart of the speculation around 3I/Atlas lies a question of physics. Could anything actually use the Sun's gravity to stop? The Oberth Effect is the key. When an object moves fastest, closest to the Sun, a rocket burn or any velocity change multiplies its impact. For 3I/Atlas approaching perihelion on October 29th at 68 kilometers per second, the math is unforgiving. To halt its escape and trap it in a permanent solar orbit, the object would need to shed nearly 32 kilometers per second of speed in a single maneuver. That's not a gentle nudge. It's an energy requirement far beyond anything natural outgassing has ever produced. Even the most active comets, venting jets of gas and dust, manage velocity changes on the order of meters per second, not tens of thousands. The Sun's gravity offers a unique opportunity. Any deceleration at perihelion is maximally efficient. But the numbers are absolute. A 20 kilometer per second slowdown, sometimes cited in popular reports, would slow 3I/Atlas, but not enough to capture it. The object would still escape the solar system, only on a slightly less hyperbolic path. Only a reduction approaching 32 kilometers per second would bind it to the Sun. Astrophysicists run these calculations with the same equations that guide interplanetary probes. The conclusion is always the same. The Oberth Effect is real, but the scale of intervention required here is enormous. If 3I/Atlas were to decelerate by even half the needed amount, it would defy every known natural process. The next phase of the investigation hinges on whether any such change is observed as the comet rounds the Sun unseen. Less than 1% of interstellar objects should ever arrive with an orbit this flat. That's not a guess. It's the outcome of thousands of simulated trajectories run by orbital analysts. Most wanderers from the galaxy cut through the solar system at steep random angles. Yet 3I/Atlas threads almost perfectly along the ecliptic, as if it had aimed for the narrowest lane. The odds are so low that some astronomers call it a statistical outlier, while others suggest it could be a sign of something more deliberate. The scientific debate splits along familiar lines. On one side, skeptical researchers point to natural explanations, a chance alignment, a product of galactic drift, or perhaps a quirk in how the solar system sweeps up debris. They remind colleagues that rare events do happen and that the universe is vast enough to produce outliers by accident. On the other, a small but vocal group is willing to consider more exotic possibilities. Avi Loeb, known for his willingness to entertain engineered scenarios, has argued in the past that not every anomaly should be explained away. While he hasn't made a direct claim about 3I/Atlas, his perspective lingers in the background. If an object's path looks engineered, it's worth asking why. Every hypothesis faces the same challenge: the blackout window. With Earth blind, the only way to separate coincidence from intention is to watch for evidence. An abrupt change in speed, a sudden course correction, or a fragmentation event. Until then, all theories remain on the table. The stakes rest on what, if anything, is observed when the comet reappears. Every measurement of 3I/Atlas comes with a margin for doubt. Hubble's imaging sets an upper limit on the nucleus, no more than 5.6 kilometers across, but the true size could be far smaller, hidden by a thick coma of dust and gas. Photometric models, built on assumed reflectivity and density, put the mass at around 33 billion tons. Yet that figure depends on whether the light is coming from solid ice, loose rubble, or simply a cloud of large dust grains. Spectroscopy reveals a chemistry heavy in carbon dioxide, 8 times more CO2 than water, unlike most comets in the solar system. Analysts point out that a body this massive, passing within 2 million kilometers of Mars, should have tugged at the planet's orbit, or at least nudged its spacecraft. No such effect has been detected. Until the nucleus is isolated or a gravitational pull is measured, every estimate remains provisional. For now, the data favor natural explanations, outgassing dust and error bars, over anything more sensational. October 29th, 2025. At exactly 1.36 astronomical units from the Sun, roughly 203 million kilometers, 3I/Atlas will reach perihelion, the closest point in its solar flyby. The object's speed at that instant, 68 kilometers per second, enough to cross the distance from Earth to the Moon in under 2 hours. No telescope on or near Earth will be watching. For the next few hours, all possibilities remain open. If 3I/Atlas continues on its hyperbolic path, it will slingshot past the Sun and vanish, never to return. But if its velocity drops, by even a fraction of what physics demands, it could become the first interstellar object ever captured by our star. No natural process has ever been seen to shed 32 kilometers per second in a single pass. The world waits, not knowing which future will be written in the Sun's glare. On October 29th, 2025, 3I/Atlas will pass the Sun at 68 kilometers per second, following a path just 5 degrees off the solar system's plane. A near impossibility for a random interstellar visitor. Every major telescope on Earth will be unable to observe the event, leaving a 16-day window where direct data goes dark. Analysts confirm that no gravitational effect was seen as the object passed Mars, challenging the highest mass estimates and raising questions about its true nature. Despite a photometric mass of 33 billion tons and a rare retrograde trajectory, no evidence proves artificial control or propulsion. Some theories point to natural comet activity, while others note the alignment and velocity remain statistically unusual. For now, the scientific record holds more questions than answers. As agencies prepare to revise planetary defense models and future missions, the outcome of this encounter will set a new precedent for how we watch the skies and what remains hidden, even in an age of constant observation.